Welcome to this introduction to spectroscopy and spectrometry, or the interaction of light with matter. This short presentation is the first of a series of videos which will attempt to introduce you to the various spectroscopic techniques that are available, the intricacies of the experimental makeup to use those techniques, and the instrumentation that is used to record the results. First of all, we start with the nature of light itself. As you probably know from previous studies, like the rest of the universe, light has a dual nature. First of all, light, meaning all electromagnetic radiation, exists as a wave classically. This means it has a wavelength measured in meters, which is the distance from the peak of one wave to the peak of the next. And those peaks travel at a set distance known as the Greek letter mu, the frequency, which is measured in cycles per second or hertz. Additionally, all radiation travels at the speed of light, which in a vacuum is a universal constant, 2.998 times 10 to the 8th meters per second. Therefore, wavelength and frequency are inversely proportional to each other. C, the speed of light, is always going to be equal to lambda, the frequency, times nu, the wavelength. So the various regions of the spectrum are defined by lambda and nu. The entire electromagnetic spectrum runs the gamut from radio waves through microwaves, infrared radiation, visible light, red, orange, yellow, green, blue, indigo, violet, ultraviolet, X-ray, and gamma ray. The longer wavelength, and therefore the lower frequency end of the spectrum, is the radio wave range. The highest frequency with the shortest wavelength is the gamma rays. Additionally, more technically, electromagnetic radiation is what's known as a transverse wave. This means as the electric field oscillates in a given direction x, it generates an oscillating magnetic field orthogonally to it in the plane that's 90 degrees away. And both of these frequencies propagate transversely to the direction of where the wave is pointing. As you can see from the following small cartoon, you have a wave of electromagnetic radiation propagating in the XY plane, basically orthogonal to both axes, splitting the plane. This means the electric field is oscillating within the XY plane. Orthogonal to that, you have a magnetic field oscillating in the YZ plane. Both of those fields progress at 90 degrees from each other in a straight line that defines the general propagation of the wave. Additionally, through quantum mechanics, you've probably also learned that light, like everything else in the universe, can behave as a particle. Everything in the universe has a dual nature. It behaves both as a particle and a wave. And through the works of Einstein and others, it was found that light has mass. This mass imparts energy into any object that the light strikes. That energy is transferred through a very simple relationship where the energy of one photon or one particle of light is equal to a constant h times the frequency, where h is Planck's constant of 6.626 times 10 to the minus 34th joule seconds. And therefore, higher frequency radiation is going to have higher energy, and lower frequency radiation has lower energy. In more depth, as you recall, quantum mechanics is defined by 4 numbers, the last one being spin. In this regard, photons obey what are known as Bose-Einstein statistics. That means the spin vector for a photon has a value of 1. In reality, spin is a vector, and the m sub s number is the shadow that that vector casts upon the z-axis. So in the case of light, where you have a spin of 1, that means it's possible for the photon to be lying directly on the x-axis, vertically on the z-axis, full up, or vertically down on the z-axis. So light can have m sub s values of +1, 0, and -1. Interestingly, these 3 spin values are seen in real life, where +1 and -1 represent oppositely polarized light, and a spin of 0 is the combined unpolarized light. As photons interact with matter, you also have to have the following realization. Matter itself is composed of atoms, and those atoms are made of subatomic particles, and all of the above can have charge. In the atom, the proton has a charge of +1, the electron has a charge of -1. Ionized molecules can form anions with negative charge or cations with a positive charge. Also, matter has a dual nature, with one major difference. Protons and electrons are what are known as fermions. They obey Fermi-Dirac statistics. This means they have a spin of 1/2, or the spin vector is 45 degrees to the z-axis. So m sub s can either be +1/2, an angle 45 degrees up, or -1/2, an angle of 45 degrees down. Both of these properties of matter have implications with how it interacts with light. Spectroscopy. Spectroscopy is the interaction between matter and light based upon the quantum nature of light. The energy of light is absorbed to create a quantized change in state of matter. However, since the spin of a photon is different from the spin of an electron or a proton, the motion itself, the angular momentum, cannot be transferred because a photon with a spin of 1 cannot interact with a fermion with a spin of 1/2. Instead, the entire energy state of matter is changed. The energy of the photon can be absorbed in increments of 0, plus or -1. This can cause changes to the electronic and the vibrational and rotational states of molecules and the electronic states of atoms. However, the spin cannot be changed. Spectrometry, on the other hand, is based upon the wave nature of light. Once again, quantum mechanically, matter is composed of spinning charged particles. Since they are spinning at an angle, they will precess through time, and the very existence of these particles creates an oscillating electromagnetic field as they precess back and forth. Electromagnetic fields will interact with each other. Therefore, the internal motions of atoms and ions will interact with the electromagnetic field of light. These interactions can be either constructive or destructive. And since light moves at a given frequency and the atom spins at a known rate, the interactions will produce repeatable and quantifiable spectrum. So, in conclusion of this overview, throughout the next series of videos, you will first of all be given a brief review of quantum mechanics, its historical derivation, and the implications that the energy of matter is quantized. This will follow through with the application in spectroscopy. You will see the derivation of different quantum states of atoms and molecules, and how the symmetry of a given state, when applied to group theory, will define what changes are possible through what are known as selection rules. Specifically, this will have applications to UV visible spectroscopy and infrared spectroscopy, which will be gone into in some detail. In the second set of videos, you will have a brief review of electromagnetic wave theory, and then in some detail again individually, how those electromagnetic waves interact with matter in various applications. Specifically, Raman spectroscopy, electron spin or paramagnetic spin, nuclear magnetic resonance, and mass spectrometry. So, thank you very much, and I hope you enjoy the rest of these videos.